All right, back for part B. We were just about to start the part on ionic bond strength and lattice energy. Remember that ionic compounds consist of a three-dimensional array or lattice of alternating positive and negative ions, and that's because the electrostatic attraction that ions have for each other when they're of opposite charges is actually something that sort of manifests itself in three dimensions. So it's not just like a covalent bond like between the hydrogen and the oxygen and water, where that attraction only goes in one direction between the two atoms, but the an Na plus ion, for instance, can attract Cl minus ions from any direction around it. And so one Na plus ion will have a bunch of Cl minus ions clustered around it. Each Cl minus ion, in turn, will have a bunch of Na plus ions clustered around it. And when you work it all out, it turns out that the overall total number of Na plus ions is the same as the total overall number of Cl minus ions, and that's why we call it NaCl. So the strength of ionic bonds is actually very similar to the idea of lattice energy. How much energy does it take to break up that three-dimensional lattice or three-dimensional array of alternating positive and negative ions? Okay, and so the lattice energy is also called delta H lattice, and it's the energy that you have to put in order to separate 1 mole of a compound into separate ions in the gas phase. So if you have an ionic compound with the formula Mx, with M being some metal and X representing, say, a halogen, like chloride or fluoride or bromide or something like that, then Mx in the solid phase being transformed into M ions in the gas phase and X ions in the gas phase. Well, the delta H, or the enthalpy for that reaction, is the lattice energy for doing that to 1 mole of the compound. Lattice energies are always endothermic, that is, they're always positive, because you always have to put energy in order to break up the lattice of an ionic compound, because those lattices form in the first place for a reason, and that's usually because they're more stable than the separate ions were before the lattice is formed. And when you form something that results in greater stability, that means you give off energy, and in order to reverse that process, you have to put energy in. So that's why lattice energies are always endothermic or positive. Okay, yeah. The amount of energy you'd have to put in to break up 1 mole of a lattice into its ions is the same amount of energy that you would get out when the ions come together to form 1 mole of the lattice. It's just that the sign would be opposite. So if you reverse this process here, bring a mole of M ions and X ions together to form a mole of Mx in the solid phase, well, the delta H for that would be the same number as delta H lattice, but it would be opposite in sign. So delta H lattice is positive. If you reverse the reaction, it would be the same number, but it would be negative. And basically, the bigger the lattice energy is, the more stable the compound is, and the stronger the ionic bonds are. There is an equation for calculating a number for lattice energy, and that is C times Z plus times Z minus over RO. C is a constant that depends on the type of lattice that's being formed, and generally that means the way the ions arrange themselves relative to one another. There are actually several different ways to do that, and we're not going to go into detail on that, but there'd be a different constant for each of those possible arrangements. Z plus is just the charge on the positive ion, Z minus is just the charge on the negative ion, and RO is the distance separating them. That is the distance from the center of one ion to the center of the other ion in the lattice, as once it's formed. And so from this, you can tell that you're going to get bigger numbers for lattice energy from larger positive and negative charges, and also from shorter distances. So bigger charges and shorter distances means more lattice energy. And shorter distances tend to correspond to smaller ions, by the way. The next topic the book covers is the Bourne-Haber cycle. And I'm going to skip this except to say basically what it is. It's a way that scientists can actually measure lattice energies. It's not so easy to measure lattice energies directly. So what we actually do is take advantage of Hess's law and find a bunch of different quantities that are relatively easy to measure. And then we arrange them together and relate them to each other in a way that we can come out with the lattice energy. And some of the things that we use, or some of the things that we measure in order to get the lattice energy, would be the enthalpy of formation of the compound, the ionization energy of the metal that's involved in the compound. Remember, these are ionic compounds, so there normally is a metal involved. The electron affinity of the nonmetal goes into it also. The delta HS, that is the enthalpy of sublimation of the metal, because you have to go from the solid phase to the gas phase in order to have a true lattice energy. So that's sublimation. D is the bond dissociation energy of the nonmetal. And that leads to the lattice energy. But we're not going to go into any other detail about it, because we really want to get to molecular structure and polarity. That's a really important thing, to be able to know what the shapes of molecules actually are. And we're leading up to that. We haven't gotten to it yet. The Lewis structures, it's important to remember as we go along, the Lewis structures only show bonding between atoms. And when you put the atoms together to form a molecule, the Lewis structure only shows you how one thing is bonded to other things in the molecule. The Lewis structure doesn't actually show you the structure of the molecule. It doesn't actually show you the shape of the molecule, or the molecular geometry is what we usually call it. We're interested in the shape of the molecule because the shape of the molecule determines whether the molecule will be polar or nonpolar, and that determines a lot of different things about the molecule's properties. Things like boiling point, melting point, density, solubility in water are all related to whether a molecule is polar or not. Also, we can guess what kinds of reactions it's likely to engage in if we know how the atoms are arranged and where there's room for another molecule to get in and start reacting, or where the lone pair of electrons might be, that kind of thing. So knowing the actual shape of the molecules is pretty important. As I was saying a moment ago, a Lewis structure is two-dimensional, and it's only meant to show how the atoms are bonded to each other. And in a Lewis structure, you can show the bonds at being basically just about any angle. I tend to draw them in the books. Most books tend to draw the bonds between the central atom and the outer atoms spread out more or less evenly around the central atom, just for neatness and convenience. But you don't necessarily have to draw them that way. If you wanted to draw a Lewis structure of CH4, we usually draw, like this, with a single bond between the carbon and each of the outer four hydrogens. But for a Lewis structure, that would be just as correct, because it shows what is bonded to what and how, and that's all the Lewis structure really needs to show. Okay. The thing is that even at best, even if you do your best to draw the Lewis structure in a way that represents where the bonds would actually be, Lewis structures are two-dimensional, and a lot of molecules in real life are actually three-dimensional, because real life is three-dimensional. And the Lewis structure isn't really very good at showing you what three-dimensional molecules look like. And as it turns out, CH4 is a three-dimensional molecule. Even if you draw this nice sort of plus-shaped molecule with carbon in the center and the hydrogens equally spaced from each other, this Lewis structure makes it look like that molecule is flat and sort of T-shaped, or like a plus sign. And it makes it look like the hydrogens are 90 degrees away from each other. That is not what CH4 is really like. And so we're going to go on in this section to find out how to tell what CH4 really is like, along with other three-dimensional molecules. The Lewis structure, as I said, allows you to put the bonds at just about any angle relative to each other, but most molecules in real life are three-dimensional, and the bonds can only occur in certain locations related to the repulsion of the electrons that are involved in the bonds for each other. And that's because since bonds involve electrons, the result is the bonding electron pairs on a central atom will get as far apart from each other as possible in 3 dimensions. And that's the part that the Lewis structure doesn't consider. And that's what determines the actual shape of the molecule. So first of all, let's talk about what bond angle actually is. Bond angle is the angle between any 2 bonds that involve a common atom. Like, for instance, in water, you've got oxygen at the center and 2 hydrogen bonds, or 2 oxygen-hydrogen bonds. The bond angle between the 2 hydrogens is 104.5 degrees. And so it's like measuring an angle with a protractor. The bond between the hydrogens and the oxygens are a certain distance apart, and they revolve around a central point, and so you can measure it in terms of degrees. And in formaldehyde, which has the formula CH2O, that is CH2O, there is a carbon-oxygen double bond and also 2 carbon-hydrogen single bonds. And it turns out that the bonds are about 120 degrees each, but actually the double bond takes up a little more space and it pushes the 2 hydrogens a little closer together, so that bond angle is actually more like 118 instead of 120. 120 is what you would expect if the 3 bonds in the molecule were equally spaced around the central atom, because a full circle is 360 degrees. And if you have 3 things that are equally spaced around a circle, you would expect them to be 120 degrees apart. But in this molecule, it's a little different because you've got the double bond taking up more space. Bond length is the distance from the center of the nucleus of one atom to the center of the nucleus of the other atom that are involved in a bond with each other. And bond lengths are usually measured either in length units of angstroms, or angstroms as we usually call it in English. The symbol is the Swedish letter A, which is an A with a little loop on top. And an angstrom is about exactly 10 to the minus 10 meters. It's not an SI unit, but it is often used in chemistry and physics because it is a very convenient unit to use for things like sizes of molecules. Because when you measure in angstroms, you get a convenient number to use. A lot of times, things like bond lengths are also measured in picometers, which is 10 to the minus 12 meters. That is an SI unit. And so that might be easier to use. And what we come to next is how we actually find the shapes of molecules. And this is known as the VSEPR theory. A lot of people mispronounce that as VSEPR, but it's actually more like VSEPR, I guess. But anyway, it's the valence shell electron pair repulsion theory. And I just call it VSEPR because I don't think it's really that hard to say. The electron pairs on the central atom of a molecule will get as far apart from each other as possible in 3 dimensions due to repulsions. And that's what the VSEPR theory is all about. Valence shell electron pair repulsion. So the electron pairs in the valence shell around the central atom will repel each other so that they get as far apart from each other as possible. And real life is in 3 dimensions, so they use all 3 dimensions. Knowing this allows us to predict fairly easily the shapes of molecules from the numbers of electron pairs, or more accurately, regions in which electrons are located on the central atom. Now, in doing this, we need to keep in mind, although this is usually a fairly minor point, that not all repulsions are created equal. A lone pair of electrons is not involved in a bond. That's what makes it a lone pair of electrons. The lone pair of electrons is entirely located on the central atom, like the lone pair of electrons in ammonia. The Lewis structure for ammonia looks like this, with nitrogen has a single bond to 3 hydrogens and a lone pair of electrons that's right on the nitrogen. Since that lone pair of electrons belongs entirely to nitrogen and it's not spread out between nitrogen and another atom, that lone pair of electrons ends up taking up more space on the nitrogen than the bonding pairs of electrons do, because the bonding pairs are spread out between the nitrogen and the hydrogen. So the repulsion between lone pairs for each other will be the greatest repulsion of all because they take up the most space on the central atom. So lone pair repulsion will be the greatest of all. Lone pair bonding pair repulsions will be the second greatest. And then the least repulsion would be bonding pair repulsions. So the repulsion between the lone pair and the bonding pair, that would be greater than the repulsion between the bonding pair and the bonding pair. That has the effect of distorting the shapes of the molecules a little bit, although it doesn't normally distort the shapes enough that we would have to change the name of the shape, for instance. But it will change the numbers of the angles a little bit. So an example where we can start out with VSEPR fairly simply is something like beryllium fluoride. Oops. Beryllium fluoride. The Lewis structure comes out like I've drawn it here, with beryllium and a single bond to a fluorine on one side and a single bond to fluorine on the other side. And since you've only got 2 areas of electron occupation on the central atom, they will get as far apart from each other as possible in 3 dimensions, which means they will be the bonds will be directly opposite each other, 180 degrees apart. And this is one case where if you draw the Lewis structure like this, then the Lewis structure is an accurate depiction of what the molecule actually looks like. Another one is aluminum chloride, AlCl3. If you do the Lewis structure, and remember, beryllium and aluminum are among the elements that are content with less than an octet of electrons around them. And so the beryllium here only has 4 electrons around it. That's okay, because it's an exception to the octet rule. Aluminum here only ends up with 6 electrons around it. But again, that's okay, because it's an exception to the octet rule. The aluminum has a single bond to each of the chlorines. There are 3 chlorines. They will get as far apart from each other around the central atom as possible in 3 dimensions. Well, actually, the furthest apart you can get them is 120 degrees. And that only requires 2 dimensions. So if you draw the Lewis structure with the chlorines equally spaced around the central atom, then that is also an accurate representation of what the molecule really looks like. Okay, and we end up naming the electron geometry or the electron pair geometry based on where the areas of electron occupation are around the central atom. And so, for example, in a case like this, where there are two areas of electron occupation or two regions of electrons around the central atom, and they're directly opposite each other, we would say that the electron geometry for BeF2 is linear. Okay, so two electron regions on the central atom, the electron geometry is linear. Okay. In AlCl3, we have three electron regions around the central atom. And again, the way you can get them as far apart from each other as possible would be to have them 120 degrees apart from each other in this sort of shape, sort of like a Mercedes emblem shape, if you want to think of it like that. This is flat and three-sided, which is why we call it trigonal planar. Okay. Trigonal planar just means flat, three-sided. Now, for this information, I'm also posting a table from another source on D2L that might explain things, I think, a little bit better than the table in the book does. There are a couple different tables that I'm posting, and so you can have a look at that too, and hopefully that might clarify some things. So be sure to look for that. Also, let's see, moving on. When you have four regions of electrons around the central atom, then things get a little more complicated. And also, the reason that I'm saying regions of electrons around the central atom, rather than pairs of electrons around the central atom, is that when it comes right down to it, double or triple bonds take up about the same amount of space as a single bond. So we would count a double bond as one region of electrons, and we would count a triple bond as one region of electrons. So that's what I mean by region. It's just like an area, a compact area where electrons are. When you have four electrons around a central atom, things get a little more complicated because things suddenly pop into in 3 dimensions. There's no way, well, no matter how hard you try, the best you can do in 2 dimensions with 4 things around the central atom is something like I drew for CH4 for the Lewis structure, which has the hydrogens 90 degrees apart from each other. And that means the electrons involved in those bonds are only 90 degrees apart from each other. And that results in a certain amount of repulsion. They don't want to be that close to each other. But if you allow things to go into 4 dimensions, you can get those hydrogens and the electrons in the bonds to the hydrogens to be 109.5 degrees apart. And that is known as a tetrahedral arrangement. And I built one here in a molecular model kit. And this is a tetrahedral arrangement. You can think of also a tetrahedron, you can make one yourself if you take both of your hands and put them together like this. And then, so the carbon would be where your 2 hands come together, and then the fingernail on nails on your first finger, your index finger, and your thumb would be hydrogen atoms. So hydrogen, 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 kind of like that. Or like this. The best way that I've found to draw by hand a tetrahedron in on a flat piece of paper is something like what I've got here, where the straight lines would be lines or bonds that are flat against the paper. The wedge going down is a bond that's coming out and down towards you. So this one here. And the dotted line is a bond that's going down and away from you. So this one in the back here. And so that's kind of a quick and easy way to draw a tetrahedron, which is, not too bad as far as accuracy is concerned. Okay, so you can see if you set the tetrahedron down on a flat surface, whoops, it stands up a bit. And so the central atom is raised up a bit from the bottom, and a tetrahedron is perfectly symmetrical. So it doesn't matter which way I put this. You can't tell the difference as long as all of the outer atoms are the same, which they are in CH4. So tetrahedron is perfectly symmetrical. It doesn't really matter which way you look at it. Now, when you get 5 regions of electrons around the central atom, things get even a little more complicated because it's 3-dimensional and not all of the positions around the central atom are equivalent to each other. This structure is known as a trigonal bipyramid, and it looks something like this. Okay, and we usually draw it with the 2 atoms that are directly opposite each other going up and down, and then the 3 atoms that are going sideways are kind of horizontal. And so looking at it like this, the way I've drawn it on the paper is kind of like this, where you've got one bond going straight up, one bond going straight down, one bond going sideways and back, and one bond going sideways and forward, and then one bond going straight to the left, like this one. And an actual example of a molecule like that would be PCl5 with phosphorus in the center. So the yellow atom would be phosphorus, and the gray and white atoms would all be chlorines. The reason I use different color atoms for different positions is, well, not only did I run out of the white spheres, but also to indicate that the positions in a trigonal bipyramid are not equivalent to each other like they are in a tetrahedron. Notice that these bonds in the horizontal positions, they're also called equatorial positions. They're 120 degrees apart from each other. If I hold the molecule like this, so we're looking directly down on it, it looks like a trigonal planar molecule. And so these atoms are 120 degrees apart from each other. But if I stand it back up again, you'll notice that the atoms that stand straight up or down and the atoms that go to the side are only 90 degrees apart from each other. So there are 2 different bond angles in this molecule. And that makes a difference. And the reason we call it a trigonal bipyramid is if you take the molecule and start filling in the sides, like you put a side here and a side here and a side here, you get a 3-sided pyramid pointing up. If you do the same thing to the bottom, you get a 3-sided pyramid pointing down. And that's where we get trigonal, meaning 3-sided, bipyramid. So it's 2 3-sided pyramids stuck together base to base. Okay. And so these positions, the equatorial positions where I have the gray spheres, have more space than the axial positions where I have the white spheres. And that's going to make a difference later on because, well, as we already said, lone pair electrons occupy more space than bonding pair electrons. So it turns out if you have a structure where the electron arrangement is trigonal bipyramid, but it has one lone pair on the central atom, where's the lone pair going to go? Is it going to go here or here, which would be equivalent to each other, or is it going to go to one of these equatorial positions? And since the equatorial positions have more space, the lone pair is going to go to the equatorial position, not to the axial positions. So we'll get to that in detail in a minute. The other possibility that we're going to cover would be, what if there are 6 regions of electrons around the central atom? Then you get something that's known as octahedral. And octahedral can maybe best be envisioned as sort of like a square with a stick through it. This is an octahedral structure. Again, you can sort of pretend for a moment that you have axial atoms and that you have equatorial atoms because of the way we draw it. We draw usually with one going up and one going down and the others going sideways. But the fact is that once again, with an octahedron, like a tetrahedron, the positions are all equivalent to each other. So I can move this around into all different positions and you can't tell the difference. So in an atom with an octahedral electron geometry, it doesn't matter where you put the lone pair. It doesn't matter where you put the first one. Once you put one in, though, the second lone pair of electrons wants to get as far apart from it as possible. So the second electron or lone pair of electrons will go directly opposite it. Okay. But that's a little bit later. A good, decent way to draw an octahedron on a flat piece of paper is kind of like this. Just sort of make an X and draw a vertical line through it. And that would be looking at it something like this, where you have a bond going straight up, a bond going straight down, and then a bond going back to the left and one back to the right, and one coming out to the left and one coming out to the right. And you can draw it with the wedges like I've drawn here for SF6, which is an example of a molecule with an octahedral arrangement. And you can see the dotted lines represent the atoms going back, and the wedges represent the dotted line or represent the bonds coming out at you. And then the straight lines represent the things going straight up and down. Okay, I see I'm a little over on part B. So we're going to have to pick up part C in just a moment.